we've seen a number of distributions, and they all have varied shapes. Here's one of the early ones we saw, distribution of incomes. You look at that and you know that the average is being dragged a little bit to the right of the median by this tail, and you can't place it very well by eye, nor can you place the SD so well by eye. Next distribution that we saw was ages of mothers who gave birth at a hospital near Berkeley, and that distribution is less skewed than the previous one, but still clearly skewed. If we look at the distribution of the weights of their babies, though, here is what it looks like. And now here, suddenly you have a very pretty symmetry. A sort of bell shape. And it turns out that there are many distributions that look like this. So typically distributions of biometric data, measurements of quantities like height, weight across large populations, head circumference, the concentration of certain chemical in the blood, and so on, some test scores. Many variables follow this kind of a distribution, but absolutely not all. Many variables don't. In fact, more variables don't than do. So here ages is one. It's staring at you. There's an example that does not follow the bell-shaped distribution. However, for those that do, it is possible to use that bell to quickly get approximations to areas in the histogram. And what we're going to do now is we are going to start out with an examination of the bell-shaped curve that underlies all such bell-shaped curves. It is the parent of them all, and it is called the standard normal curve, and it looks like this. A beautiful symmetric bell centered at 0, and now let's take a look at this horizontal axis. What have I called it? Z. Yep, you're thinking standard units. You should be thinking standard units. Indeed, centered at 0 as it should be, plus minus 1, plus minus 2, plus minus 3, and not a lot outside. Very much like standard units are supposed to behave. This curve has an equation, and that's a lovely equation. Mathematicians love this thing because look, square root of 2, pi, e, all the wonderful numbers of mathematics. Z goes from minus infinity to plus infinity, so all the way to the left, all the way to the right, but it doesn't look like that, does it? It doesn't look like that because the curve falls off so sharply that once you've got past about 3.5, you can't really see it on this scale. That's how standard units behave. So when you look at this curve, you should be thinking standard units. And that is why the letter Z has been used consistently. The curve is a function of z squared. What does that mean? Its value when z is equal to 1 is exactly the same as its value when z is equal to minus 1. Because the square of 1 is the square of minus 1. Its value for z equals 2 is the same as the value for z equals minus 2, because the square of 2 is the same as the square of minus 2. Both of them are 4. And that's why you have the symmetry. And for those of you who understand the exponential function, you will see e to the minus z squared is why it is dropping off as it does. Now there are a few facts to understand about this curve. The total area is 1. That requires proof, and I'm not going to prove it here. Some of you might have seen it in a calculus class. The balance point is 0. This is evident, though even that requires a bit of a proof. The points of inflection are at minus 1 and plus 1. Now what is a point of inflection? You can see this curve starts out sort of coming down and then sort of drops to going up. So we say in high school American math talk, from dropping water to holding water. And there is a point where that behavior changes. And those points are respectively minus 1 and plus 1 on the curve. So about there and about there. That is going to be a useful observation when we put down standard deviations on bell-shaped curves, because by now you should be thinking, well, the SD of this curve is 1. If I imagine this to be a histogram, then the SD's got to be just about 1. Now, if it's a histogram, if we ignore that we've got standard units on this side, if it's a histogram of heights or weights, something we're going to be interested in is what percent are in any given range. So we're going to want to find areas under this curve. Now, those of you who have done some calculus will say, fine, I'm just going to integrate this thing. A remarkable feature of this curve, though, is while we know that the integral in any interval must be finite, in fact it must be less than 1, there is no formula in closed form for the integral of this curve from point A to point B. That's a rather deeply philosophical statement. There is no formula in terms of what? Well, in terms of your usual standard functions, the polynomials, the exponentials, the hyperbolics, and so on. It's not that you can't do it, or I can't do it, or the maths department on campus can't do it. It can't be done. It can't be expressed in terms of a standard set of functions. That's a very, very deep result. And where does that leave us? We still need the areas. So if we can't integrate, then what? Well, then you approximate. You approximate, and there are many, many, many wonderful approximations of this curve and the areas underneath it, one of which is in your textbook. And so we're going to move now to a fun applet in your textbook which allows you to find any area under this curve that you choose to find. Okay, Mauricio, start now. Here is the normal curve applet in your text. The standard normal curve, your text calls it the normal curve, the one, the ancestor of them all. There are others which we'll talk about later, but for now it is the single normal curve. Center 0, points of inflection at plus or minus 1, 2, 3, and you can see not much happening outside that, outside the range. Oh, minus 3.5 to 3.5. Beyond that, on this scale, you can't see much. Now, what I've done is I've selected a lower endpoint of minus 1 and an upper endpoint of plus 1. And what the applet does for me is that it shades the interval in between and tells me the area. So what you're saying is that in between minus 1 and 1, the area is just over 68%. If I wanted to look at minus 2 to 2, I would convert my endpoints, and I would get an area of 95% roughly. So if in your head you are thinking of this as the mean, you should be, that's a good idea. If you're thinking of 1 as the SD, you should be, that's also a good idea. Then what you're learning is that in the range mean plus or minus 2 SDs under the normal curve, you pick up about 95% of the data. Remember, Chebyshev had told us that it has to be at least 75%. For the normal curve, it's in fact quite a bit more. It's 95%. Can you do anything else? Sure. You can drag the left end down as far as it'll go, and you can move your right end to wherever you want. So let's bring it down to 1.083, just to pick a number out of the blue. And if I hit return, what I learn is that the area to the left of 1.083 on this curve is just about 86%. Another way of saying that is that 1.083 is roughly the 86th percentile of this curve. If you're thinking of this as an axis in standard units, then that 1.083 is a value in standard units, so that 86% are below that value. And so let us see, shall we try to find, say, the 95th percentile? Why don't we? So to find the 95th percentile, I must drag my right end a little bit more, and as you know, I'm really bad at this. 96, not so bad. I'm going to come down because, yes, I know the answer. I'm going to go to 1.65. That's awfully close. So I'm just going to say that the 95th percentile is 1.65. I think you might be able to do better by 1.645, might you? Yes! 1.645, exactly so. But really, I will stick with 2 decimal places for now. and use 1.65 as my 95th percentile of the curve. This is all rather technical. What is it telling me? It is telling me that if this were a distribution of some physical quantity, then a value that is 1.65 standard deviations above average is the 95th percentile. That is, 95% of the data are going to be below. You are used to using these applets by now, and so I think you will know how to use it when you have numbers of your own to enter. I'll remind you that under the normal curve, some useful things to remember are in the range -1 to 1, you have about 68% of the data. That is just over 2/3. In the range -2 to 2, you have just around 95%. So let's make a list of some values that are useful to remember. Central areas between z equals -1 and +1 we said was about 68%, just over 2/3. Between -2 and +2 was about 95%. If you know the central area, you can exploit the symmetry of the curve to find tail areas. If between -1 and 1 I have 68%, then outside that range I have 32%. Since the curve is symmetric, each tail has 16%. Equally, each tail, the one to the left of 2, the one to the right of 2, are about 2.5%, because in between -2 and +2 you have 95%. Percentiles, we saw one. The 95th percentile we saw was 1.65, roughly it was 1.645, but I'm not dealing with 3 decimal places at the moment. By symmetry, the 5th percentile is -1.65. So what? So we are playing with a curve that is entirely in standard units, but I'm not interested in standard units in the end. I want data that have a physical meaning and that have units of measurement. And so what we're going to do in the next few segments is we're going to build up to using this standard curve as the basis for finding areas under bell-shaped curves of data.